Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous two lectures we were discussing about hydrologic system for the purpose of hydrologic analysis. We have discussed about general hydrologic system model, which is considered as a linear model. So, if we are analyzing the hydrologic system considering it as a linear system, we need to have understanding about linear system theory. So, that we have discussed in the previous lecture. If we are considering the hydrologic system as a linear system, then the system will be following the principles put forward by linear system theory. So, that way we have gone through two different principles which a linear system should follow, that is principle of proportionality and principle of superposition. After that we have gone through three different input functions and the corresponding response function, that is the impulse input, step input and the pulse input. What is meant by these three inputs we have studied. After that the corresponding outputs or the responses from the system, that is the impulse response function, step response function and also the pulse response functions. These we have discussed in detail. We also understood the relationships between these three response functions. Today let us move on to the topic of hydrograph analysis, in which we are going to consider hydrologic system as a linear system. So, definitely in this analysis we will be following linear system theory. That is why we have gone through the basics of linear system theory in the previous lecture. Now, let us start with today's lecture. So, we know when rainfall or storm for a short duration occurs on a catchment, it produces a runoff at the outlet of the catchment. So, we are going to consider a storm which has occurred for a certain time duration. We are not talking about the total amount of rainfall. We are going to consider a storm which is having a particular duration. If the rainfall intensity is more than that of the infiltration rate and it prolongs for some time, definitely there will be a runoff taking place at the outlet of the catchment. So, here when we are discussing about the rainfall, we are going to consider rainfall having certain duration. So, definitely it will be producing a runoff at the outlet, and the temporal distribution of the runoff we have studied by means of storm hydrograph. In the previous module we have discussed about storm hydrograph, in which runoff or the stream flow is plotted against time, that is known as the storm hydrograph. Different components of the hydrograph also we have covered in that lecture. So, temporal distribution of the runoff or stream flow is represented by means of storm hydrograph. Different ways of estimating direct runoff we have seen. In all those cases, either the runoff depth or the runoff volume we have calculated. In those cases, we were not representing the time distribution of the stream flow or runoff. But in the case of storm hydrograph, we are considering the time distribution of runoff. That is very much important when we were planning about some hydrologic project. So, different methods are there for modeling rainfall runoff processes. Some of the methods focus on modeling the rainfall runoff process due to short duration rainfall resulting into a storm hydrograph, that is known as event based rainfall runoff model. That is, we are going to consider a rainfall event. That event will be of severe event. Depending on the severity of the storm, we will be choosing a particular rainfall event, and based on that we will be understanding the impact of that particular event on the water resources system. So, in such cases we are studying the runoff which is produced due to this storm. So, a particular event is chosen and the impact of that is studied. So, those type of studies are termed as event based rainfall runoff models. Especially in the case of flooding related studies, we need to look into event based rainfall runoff models. In such cases, we will be choosing a particular rainfall event which is having a certain duration, which may be a severe event. That event will be chosen for modeling the runoff. So, such modeling studies are termed as event based rainfall runoff model. This provides the information about the variation of runoff with respect to time. Variation of runoff with respect to time means we can get from the beginning of the storm till the time entire catchment contributes water to the outlet point, we will get the results related to runoff. So, we can understand the magnitude of peak runoff, we can understand the time to peak. All these matters a lot whenever we are going to study a particular flood event. So, in such cases we will be choosing an event, rainfall event which is having certain duration, and event based rainfall runoff modeling will be carried out to understand the peak runoff and also time to peak. These are very important for hydraulic design and flood management. If you are planning for certain flood management strategies, we need to have the idea about time to peak flood and also magnitude of the peak runoff. Based on that, for different areas, different types of flood management strategies need to be proposed. So, for that we need to have an accurate rainfall runoff model based on events. We will be going for choosing event based rainfall runoff models in such cases. And when we were discussing about the time to peak runoff and the magnitude of peak runoff, so we need to have some idea about time characteristics of storm hydrograph. So, for that we are first considering a rainfall event. The event is chosen in such a way that it is an isolated event which is having a certain duration. Rainfall will be occurring for long time, continuously it is occurring. So, entire period what is the rainfall we are not looking into, we are choosing certain event, rainfall event or storm event for a particular duration. A simple event which is having a uniform magnitude is shown here. This is representing a rainfall hydrograph which is having a duration of TR. Because of this rainfall which is having a duration TR, there will be a runoff at the outlet. So, that can be obtained by means of some stream flow measurement that can be plotted as a storm hydrograph. So, duration of the storm which we are considering is TR, and this is the storm hydrograph. This figure we have already seen before while explaining about the characteristics of storm hydrograph. So, here the same hydrograph is used for the explanation of time characteristics of storm hydrograph. This is a smooth curve. Actually, what is this hydrograph? Hydrograph is the curve representing the time distribution of runoff at the outlet of the catchment. The flow contributed by the catchment at the outlet is measured and plotted. So, depending on the type of the catchment, the flow which is reaching, outflow which is occurring at the outlet of the catchment will be different. It may not be always a smooth curve as shown in this figure. It will be having certain fluctuations present because different areas will be contributing runoff at different times. So, after certain time of the occurrence of the rainfall, majority of the areas will be contributing water at the outlet point. So, because of that, the hydrograph will not be a smooth curve, certain fluctuations will be present there. But for understanding purpose, we can consider a smooth hydrograph like this. So, in this we have studied different components. AB and EF represents the base flow recession, that is AB is the part of the hydrograph which is the contribution coming from the base flow. It is not due to the rainfall. So, that is the contribution from the base flow and that is represented by AB. When the hydrograph is rising, that is representing the rising curve where the contribution from the storm has started. So, here BC is the rising curve and CPD is the crest. Crest represents the part of the flow or during that time majority of the catchment starts contributing to the runoff and it consists of the peak also. Peak of the hydrograph is also present in this particular area. And after that what will happen when it reaches the point D is representing the point of inflection which is corresponding to the maximum storage. All the storage components are satisfied. After that the contribution from runoff to the channel or the overland flow might have ceased and withdrawal from the storage components will be taking place and that is the beginning of the recession curve. And once it reaches E, entire runoff component is stopped and EF represents the contribution from the base flow. So, this is the storm hydrograph which we have seen in the previous module. So, here we are going to understand the time characteristics of the storm hydrograph. So, TR is the duration of the storm which is caused runoff at the outlet. Because of that storm event, how much is the runoff produced along with the base flow is plotted over here as a storm hydrograph. So, this is the time base of the hydrograph. Time base means we know there is some contribution coming from the base flow, groundwater contribution to the stream that we are deducting and the remaining hydrograph which we are obtaining will be having a time base that is represented by the time base TB of the hydrograph. That is from where the runoff starts and runoff ends within that time. That base period of the hydrograph is the time base. So, next is the time to peak. Time to peak is nothing but the time elapsed between the peak runoff and the beginning of the runoff. This point B is representing the beginning of the runoff and the time base between the beginning of the runoff to the peak runoff. Peak of the hydrograph is representing time to peak. TP is the time elapsed between the beginning of the runoff to the peak runoff. That is the time elapsed from the beginning of the rising limb to the peak discharge. That is what we have marked over here. Next is the time lag. Time lag is the maximum time taken by the water to travel through the catchment. So, we have studied about time of concentration. It is the time taken by the water droplet to travel from the remotest point to the outlet point. So, it is similar to that of time of concentration. It is not exactly the time of concentration. So, it is the maximum time taken by water to travel to reach the outlet of the catchment. Actually, this is calculated based on the time elapsed between the centroid of the hydrograph to the centroid of the storm hydrograph. But it is not that easy to find out the centroid of the storm hydrograph. Then what we will be doing? We will be finding out the peak of runoff when it is occurring, that time minus the centroidal time of the hydrograph. So, how we will determine this time is by considering the centroid of the hydrograph and the point where all the catchment contributes water at the outlet, that is the point of inflection D. All the storage components will be satisfied at that time. It represents the maximum storage, that is the point of inflection. So, we will find out the time elapsed between the centroid of the hydrograph and the point of inflection. So, this is represented by TL, time lag. Again I am repeating, it is the time elapsed between the centroid of the hydrograph and the centroid of the storm hydrograph. Since it is difficult to determine the centroid of the storm hydrograph, we will consider the point of inflection where all the storage components are satisfied. That point is representing the maximum storage, and the time elapsed between the point of inflection and the centroid of the hydrograph is considered, and that represents the time lag. So, these are the 4 important characteristics related to time whenever we talk about storm hydrograph. First one is the duration of the storm, TR. Second one is time base, the time represented by the base of the hydrograph, that is the base of the direct runoff hydrograph. Time to peak TP and time lag TL. So, you should carefully understand the difference between all these. TR is not an issue, it is the duration of the storm, and time base is also very clear. Time to peak is the time from the beginning of the recession limb to the peak runoff. Then slightly complicated definition is related to time lag. It is nothing but the time elapsed between the centroid of the effective rainfall hydrograph to the point of inflection. For that you need to understand point of inflection carefully. Point of inflection is the representing the time at which the maximum storage has reached or all the storage components are satisfied within the catchment. After that, what will happen? The contribution from overland flow will be ceased and withdrawal of water from storage components will be taking place. Now, let us move on to hydrograph analysis. Hydrologic analysis we will be doing by making use of the principles of hydrograph. Mainly I am focusing on the hydrograph analysis. Hydrologic system can be modeled by means of many approaches. So many different techniques are there for modeling a hydrologic system. Out of that, unit hydrograph approach is one method. So here in this module we will be discussing about the unit hydrograph approach which can be used for rainfall runoff modeling. In this, the rainfall, that is we will be considering the effective rainfall. Effective rainfall is the rainfall which is obtained after detecting the initial abstractions and the infiltration, which is contributing towards the runoff or the overland flow. That is the effective rainfall. That we will be extracting from the total rainfall. That will be acted on the watershed and it will get translated to runoff at the outlet of the catchment. That is termed as the direct runoff. That is, effective rainfall gets translated to direct runoff at the outlet of the catchment. So, unit hydrograph can be considered as an operator. That is, we have seen in the previous lecture that if you are considering a system, there is a transfer function which translates the input to the output. So, that transfer function in this case is the unit hydrograph. It is the operator. We are having the effective rainfall. This PT is representing the effective rainfall after detecting the abstractions which is acted on the catchment. Here the transfer function is the unit hydrograph. It will be converting the input PT to QT. The effective rainfall is converted to direct runoff hydrograph. QT is representing the direct runoff hydrograph. So, now let us look into unit hydrograph. What is meant by unit hydrograph? The principle of unit hydrograph is proposed by Sherman in the year of 1932. This is a very simple model which is working based on the linear system theory, which produces the direct runoff at the outlet of the catchment by making use of linear system principles more or less accurately. Even though the catchment is not behaving as a linear system, we are assuming that the catchment can be considered as a linear system, because we know the processes which are taking place within a catchment is not linear, very complex, very dynamic, which has to be represented by means of nonlinear equations. But here the main assumption which we are making is system behaves as a linear system. First, let us start with the definition of unit hydrograph. Unit hydrograph is defined as a direct runoff hydrograph resulting from 1 centimeter of excess rainfall generated uniformly over the drainage area at a constant rate for an effective duration d hours. So, this is the definition of the unit hydrograph. Unit hydrograph is the direct runoff hydrograph produced from a 1 centimeter rainfall which is occurring uniformly over the catchment or the drainage area for an effective duration or for a specific duration d hours. What do you understand by this definition? That is, the catchment is experiencing 1 centimeter rainfall. The duration of the rainfall is considered as d hours. For d hours, it can be 1 hour, 2 hours, 3 hours, anyway whatever it is. So, for d hours we are having a uniform rainfall having a depth 1 centimeter which is acted upon the catchment uniformly. Entire catchment is experiencing 1 centimeter rainfall for a duration of d hours, and the runoff produced by this rainfall, that is dr 1 centimeter rainfall is producing a runoff at the outlet of the catchment. That is what is termed as the unit hydrograph. That runoff which is produced at the outlet of the catchment is the direct runoff. That direct runoff hydrograph produced due to 1 centimeter of rainfall for d hours which is uniformly experienced by the catchment. In the previous lecture, when we were discussing about different inputs to a linear system, we have seen 3 different inputs, right? That is impulse input, pulse input, step input. Impulse input was the input which is acted upon the system instantaneously, and the step input was the input which is applied on the system in which the rate changes from 0 to 1 at time t is equal to 0 and it continues indefinitely. The third one was the pulse input. Unit pulse input is defined as the input which is acted on the system for a duration of delta t. Can you compare this 1 centimeter rainfall for d hours with that pulse input? There, in that case, 1 unit of input, whatever be the system, whether it is hydrologic system or any other system, 1 unit of input for a specific duration delta t was acted upon the linear system which is producing an output which is termed as unit pulse response function. Here also the DRH which is produced due to 1 centimeter of effective rainfall uniformly acted upon the catchment for a specific duration of d hours. These two can be compared to each other. So, this unit hydrograph is the unit pulse response function of a linear hydrologic system. In the general way, we have discussed the unit pulse input is producing unit pulse response function. Here our system is the hydrologic system. So, this unit hydrograph is nothing but unit pulse response function of a linear hydrologic system. So, this is a simple model used to derive hydrograph resulting from any amount of excess rainfall. Since this is developed based on the linear system theory, we can make use of principle of proportionality or principle of superposition for finding out the hydrographs from any amount of rainfall. We can schematically visualize that. So, this is the figure which we have seen while explaining about the pulse response function. We were having a unit input, pulse input for a duration of delta t. The response produced was represented by ht, that is nothing but the pulse response function. Here you can compare it with the unit hydrograph concept, that is we are having 1 centimeter rainfall for a duration of d hours which is acting. Then I am going to the definition. which is uniformly applied over the drainage area for a duration of d hours. 1 centimeter rainfall for a duration of d hours uniformly applied over the catchment or the drainage area. So, same way here we can consider for dr duration 1 centimeter of rainfall, it can be considered as a pulse input and that will be producing an output. Here in this case it is the runoff, direct runoff, because we are considering the effective rainfall of 1 centimeter for a duration of d hours. So, it will be definitely producing the direct runoff at the outlet. So, that is represented by our DRH, which is represented by H of t. This green curve is representing the direct runoff hydrograph. So, this is exactly same as that of the pulse response function which we have seen while explaining the linear system theory. So, for understanding this, we have gone through the linear system theory in detail in the previous lecture. Now, we need to understand the assumptions made in the hydrograph theory. First one is linearity hypothesis. Linearity hypothesis you can understand. Catchment, if you are assuming it as a linear system, it should behave as a linear system. Actually, it is not linear. For example, if you are having so many storage components present in the catchment, then system cannot behave as a linear system, because initially the storage components have to be satisfied. After that only runoff will be produced at the outlet. So, if you are assuming the processes to behave as linearly or the system as a linear system, then it will not happen.